10 o'clock in the morning on all my digital devices, so I propose that we start this session. My name is Remco Veltkamp. I'm from Utrecht University. I'm chairing this session on medical applications. We have 3 presentations. Each presentation is for 15 minutes. We have some Slack. We also have some time for questions. If you have a question, you can raise the hand in Zoom, but I will wait until giving time for questions till the end, so as not to disrupt the presentation itself. But we can see if I can keep track on the order in which the hands were raised. If you have a question at a specific slide, please also note which slide exactly. I don't know if there are slide numbers, but if so, make a note on the slide number so that you can refer to that. And everything will also be recorded and made available on Discord. And there you can also discuss after the session. Yeah, so let's start this session with the 3 presentations. Let me see. The first presentation is given by Chen Li, and the presentation is about attention-based nested UNet to exploit full resolution features for medical image segmentation. So please, Chen, if you can share your screen.
Okay.
Then we can see your slides. I can see them now.
Can you see my slides?
Yes, we see your slides. So please go ahead.
Okay. Okay, thanks for the chair. Hello everyone, I'm Chen Li. I will present our work, attention-based nested unit to explore full resolution feature for medical image segmentation. Before share our work, we want to introduce the medical image segmentation. Generally, segmentation means dividing into separate parts or segments. During the medical image segmentation, different tissue has similar image prosperities, such as threshold, contrast, or HU views. And these prosperities are divided into different segments. Due to the particularity of medical images, compared with natural images, medical images have characteristics such as great unevenness, large contrast changes, and noise. In image segmentation, UNIT and FCN are well known. UNIT and FCN are very similar. Their structure uses a more classic idea, that is encoder-decoder. It was proposed by Hinton and published on the Nature. However, the main role of the encoder-decoder structure was not for segmentation when it was proposed, but for compression of image and denoising. UNIT was proposed later than FCN. Compared with FCN, UNIT is completely symmetrical. That's to see the left and the right side are very similar. And this architecture is what we would like to introduce. In recent years, many segmentation problems will first use UNIT for basic experiments and then make some changes for certain aspects. The same is true of our work. As you can see, this is a high-level overview of our network. So frankly speaking, there is no fundamental innovation of UNIT architecture in our work. We just added some new models and methods to it to get a better segmentation performance. First, we learned that the attention mechanism can give the network ability to distinguish and focus. So we studied to think about how to implement and add this mechanism to the unit architecture. We have referred to the previous work and designed the attention gate. The attention gate performs well in selection and can enhance the learning of the target area related to the attention to the task. Meanwhile, it also can suppress the area where has no relationship with the task. Therefore, we want to integrate the attention gate into our unit architecture to improve the efficiency of propagation semantic information. So in order to make the future extracted at the different layers can be merged with the focal selection, we redesigned the skip connection, and as you can see, the attention gate is added between the convolution blocks. We take the first layer as an example for explanation. The network transferred the extracted feature from the encoder to the decoder through descent skip connections for integration of representation under selection. Because of the descent skip connection designed between nested convolution blocks, our work ANUnet can obtain full resolution feature maps at different semantic levels from the blocks. In order to make full use of this semantic information, we decided to introduce deep separation to ANUnet. We add one-by-one convolution layers and the signal activation function after every output block in the first layer. Then our work connects these layers directly to the final calculation of loss and the backpropagation of area. Besides, we redesign a hybrid loss function combined with soft dice loss, local loss, and binary cross entropy loss. About is all the network architecture design, and finally we began to think about the implement problem. We used the ANUnet L1234 to denote network tuned at 4 different depths, where the region in gray means this block and the attention gate are removed during inference. It's easy to find out that during the inference, removing these gray parts has no influence on the pioneer output because the input images will only propagate forward. However, during the training phase, there is both forward and back propagation. The gray part will help the other part to update the weight when the area is back propagated. And the final question is, how can we select the extent of the model building? We believe that the extent of model building is weighed by evaluating the performance of the 4 subnetted work L1, 2, 3, 4 during the validation. And then we conduct some experiments on 2 public benchmark datasets. They are LITS dataset and the chaos dataset. These 2 datasets covering organs from common medical images, including CT and the MRI. And the 4 indicators are used to evaluation. So compared to other methods, we can find that the performance of our work is the best in these 4 indicators. As you can see in the first table and the bottom left figure is the liver CT image segmentation task. Compared to attention unit, our work achieves the IOU increased 7.99% and the dice increased by 3.7% and the Perception increased 5%, recall increased 4% over unit. And to the right side is the kidney MRI image segmentation. Our work achieved IOU increased 4.06% and dice increased by 2.13%, and the perception increased 3.44%, and the recall increased 0.82% over unit plus. And the bottom two figure, as you can see, we use red-green to show the ground truth, and the output of our work is displayed in a blue region, and the unit or other method, the output of other method is in a green region. The prediction missed area is highlighted with the red arrows. So in the split MRI image segmentation, as you can see in the left side, our network achieved IOU increased 6.06%, and the dice increased by 3.21%. The perception increased 3.99%. Recall increased 2.43% over the attention unit. And finally, in the liver MRI image segmentation task, our work achieved a similar result. So when it comes to the attention learning result, we can find the bottom figure. Figure B1 to B10 are the attention coefficients in the first layer of the attention gate in the different training periods. We can find that attention coefficient gradually changes when training. Weights in the target organs were related to the segmentation task is enhancing, as we can see in the red region. And another part, the blue region, means the weight in the confusion tissue where unrelated to the segmentation task is suppressing. So as for experiments for model building, we used ANU 1234 to perform the same liver CT image segmentation task divided. As we can see from the table the segmentation performance of L1 is not so ideal because it's too shallow. Besides, the result also show that the performance of L3 is closest to the L4. So there is no need to use AN unit L4 during testing. A light network is enough, so we can save at least 75% of parameters amount if we use L3. Model pooling can significantly reduce the model parameters and the prediction time, but at the sacrifice of segmentation performance. So our work has been supported by the following 3 projects, and thank them here. So if you think our work is helpful for you, or if you meet some problems, please contact us. And we are grateful to help everyone to discussion. So that's all. Thank you for your attention.
Thank you very much, Chen. We have ample time for questions or discussions or remarks or criticism or any other comment. May I invite the participants to pose a question? Is there any question? Maybe I have a question to start
Okay.
with. And could you say again what is the the main difference between your architecture of the network with respect to combining the attention graph and the UNet? Did you do some additional change to the architecture of the network?
I think your question is what's the difference between our architecture between the attention unit architecture? Is that?
Yeah, so you use the UNet in combination with attention network?
Yeah. Okay.
But did you make additional changes?
The original attention unit architecture is the classic, is based on the classic unit. But in our work, our unit is based on the nested unit network. As you can see, I will show the architecture. Wait a minute.
Okay, so it is the nested thing that is new. So these escape.
Yeah, you can see the central of our network is the nested architecture, but in the attention unit, there is no such design. And our work with this nested architecture is also referred another previous work.
All right, so what is the advantage of this nested architecture?
Sorry?
What is the advantage of this nested architecture?
Okay. Your question is what the disadvantage of our network is that?
The advantage, the benefit.
Benefits, okay. As I can see, the benefits of our network is that our network is the end-to-end architecture. So there is no else pre-training or other processing steps. We just need to input the image to our network and we can get its mask. There is no other steps or other process. Okay. Is my answer solve your question?
Yeah, thanks. Does it also help to make? Does it also help to make the method more robust against noise?
Sorry.
Does the nested architecture also help in making the method more robust to noise?
To noise. Okay. Actually, frankly speaking, what you said is what we are doing now. There is no much special design for robust. We take this architecture experiment on liver city segmentation and MRI dataset. There is no other design for robust. But what you see is what we are doing now here. And thanks for your suggestions.
All right. Are there any other questions by some of the participants?
I'd like to ask a question if it's fine.
Yes, please.
Okay.
So how does the nested architecture help in generating a full resolution segmentation?
Sorry, do you mean how our nested architecture to explore full resolution?
Yes.
And okay, let's back to the architecture. As you can see in this architecture is the end-to-end architecture. So we input the image. The resolution of the input image is the same, equal to the output resolution, and there is no changes. And in the nested architecture, there are 5 layers. In the 5 layers, each layer has its own resolutions, but it's very symmetrical. In the decoder and the encoder part, the symmetrical convolution blocks is very similar, and the resolution of its 2 blocks is equal.
Okay.
Okay, thank you.
Thank you.
Thank you very much. Are there any other questions? You may either unmute your mic or raise a hand to draw attention. If there are no further questions, then let's thank the speaker.
Okay, thank you, everyone.
Thank you very much.
Thank you, everyone.
Nice work. And we move on to the next presentation. The next presentation is by Ling Chao Guo.
Yes.
You are there.
I'm ready.
Very good. Can you also share your screen
Okay.
so that we see your presentation?
Can you hear me?
Yes, we hear you, and we also see your slides, so that is very good.
Okay.
It is nice to introduce you. So
okay.
the second presentation in this session on a medical application. It's also about segmentation. It's a binary server smoothing for abnormal lung segmentation. Ling Chao, please go ahead.
Okay. Hello, everyone. My name is Lin Chao Guo from National University of Defense Technology, China. The title of my presentation is Binary Surface Smoothing for Abnormal Lung Segmentation. Accurate lung segmentation in HRCT is important for lung disease diagnosis. However, abnormal lungs, such as that with interstitial lung disease, ILD, contains high intensity in peripheral areas. Due to the presence of anomalies, the binary surface generated from cause segmentation is usually uneven, corresponding to the existence of some isolated components in 2D CT size, which makes lung segmentation inaccurate. In fact, the real lung surface is quite smooth, since anatomical structures usually do not appear sharp edges. But the binary surfaces generated from abnormal lungs with ILD are uneven and contain sunken holes. Besides, the smoothness varies between abnormal lungs with different severity. Therefore, a uniform smoothing filter with the same scale is not suitable for all lung surface models. Generally, for abnormal lung segmentation, some methods repair the poor segmentation by post-processing methods or enhance the high intensity anomalies. For surface smoothing, current surface smoothing methods usually remove the undesired noise in surface to achieve a relatively smooth surface. This work is inspired by double edge effect in Laplacian of Gaussian. The left figure shows the intensity first derivative and the second derivative near the edge of 2D gray image. It can be seen that the edge of image is the extreme point of the first derivative corresponding to the 0 point of the second derivative, called zero crossing. Then the edge of image could be delineated if only the zero crossings were found. In order to make the exposition clear and intuitive, we delineate 3 isolated circles. After performing log, double widened edges appear in the image, and the pixel values of the bright edge are positive, And then those of the data edge are negative. So the outside the double edges are all 0. And then the width of the double edge is determined by standard deviation sigma of Gaussian belt. With the increasing value of sigma, the outer edge would surround the 3 circles and connect all the isolated components. Therefore, here the edge detection is not our focus, and our goal is to connect the 3 isolated circles. But how to automatically select an optimum sigma that connects the 3 isolated circles is also our focus. Here, Hausdorff distance and average Hausdorff distance are used to detect the connection between circles with different sigma. As can be seen in left 2 figures, the 3 isolated circles have been connected with sigma is 2.1. Subsequently, the field connected component consisted by 3 connected circles will be enlarged uniformly. Therefore, the optimum standard deviation sigma is 2.1. And the field connected component is enlarged around the 0 crossing edge and expected to be eluded to the 0 crossing edge. The final result of connected circles is shown in right figure. This is our flowchart of the automatic line segmentation method. We first extract the binary line by use of thresholding technique and eliminate airways based on spatial contiguity of airways. Then we further smooth the line surface generated from cross segmentation by employing the closed double surface-based smoothing method. Finally, we achieve the accurate segmentation results by combining the smoothed line mask with original lines. The results of cross line segmentation are shown in bottom figures, and some isolated components exist in the bottom of line due to the presence of high attenuation patterns. And the 3D binary line surface is also uneven, must be smoothed by additional post-processing. Generally, there are more than 200 slices in whole CT scans of line. We post-process the binary line in foreign data in consideration of the spatial contiguity of line. We extend the Laplacian of Gaussian to 3-dimensional space. After performing 3D log in 3D line mask, a double surface effect is generated instead. Similarly, the pixel values of bright surface are positive. Those of dark surface are negative, and those outside the double face are all 0. The width of double face is determined by sigma. In order to speed up the processing, we improve the procedure of Laplacian of Gaussian and directly extract the double face where it is not equal to 0 in 3D log image. And here, the average HD is used to evaluate the smoothness of binary line surface with different sigma. With increasing value of sigma, the line surface will gradually become smoother, and the average HD will decrease accordingly. the lung surface is sufficiently smooth when average HD is approximately constant. The corresponding sigma is selected as the best standard deviation. Next, the upper figures represent the results of lung surface smoothing with typical mild ILD. Sigma is 2. The lower figures represent the result of lung surface smoothing with typical severe ILD. Sigma is 3. It is intuitive that our proposed method provides perfect performance of surface smoothing for abnormal lungs with ILD. These are the segmentation results of 4 slices from typical mild ILD and severe ILD by 3 methods and experts. It is apparent that our proposed method obtains accurate lung segmentation results for the abnormal lungs with different kinds of ILD, and the other 2 methods can identify the normal areas with low intensity, but almost lose all the details of abnormal areas. This table shows the performance metrics for normal and abnormal lungs. For normal lungs, 3 methods behave well. For abnormal lungs with different severity, our proposed method achieves the best results compared to the other 2 methods. In order to speed up our method, we analyzed all CT scans. The average HD between surfaces in 10 abnormal lungs have converged when sigma is 3, and the minimum running time of our method with fixed sigma is 3 is 0.73 seconds per slice. Also, we presented a simple and effective surface smoothing method called double surface-based smoothing for abnormal lung segmentation. Our method can remove noise while filling holes to smooth the lung surface. Meanwhile, by comparing average HD between surfaces with adjacent sigma, our method can adaptively select an optimum smoothing field to refine the uneven areas, achieving the accurate results of segmentation. The experimental results show that our proposed method can improve the accuracy of lung segmentation and will be useful for developing computer-aided diagnosis system for ILD. Okay, that's all. Thanks for your attention.
Thank you very much. I'm looking if there are any questions. Is there any from any of the participants in this session? Does someone want to take the microphone or raise a hand? Maybe, Lin Chao, you can explain to what extent this method is specific for lungs.
Yes.
Or does it also work for other organs?
Because our dataset is from the second Xianyang hospital, and they are all lungs. But I think our method is useful for other organs because their anatomical structures is similar.
So also the distinction between, say, normal lungs and abnormal lungs
Yes.
is maybe not important here. Does it also work for normal lungs?
Oh, here we test both normal and abnormal lungs.
Okay, okay. Is it possible to sort of have a ground truth for establishing the quality of the method?
Sorry.
Sort of a golden standard, a ground truth.
The ground truth is created by our expert
Okay.
from hospital.
Okay. A single one, or is it merged results of multiple annotators?
Just one.
Okay. Does someone else have a question? No further questions? Then Ling Chao, thanks again for your presentation.
Okay, no sense.
Thank you very much. And we move on to the third and last presentation in this session. The presentation is given by Magdalena Schwarzel. It's about interactive model building for volumetric data of complex cells. We have already a shared screen ready, so please, Magdalena, take the floor.
Hello, I'm Magdalena Schwarzel, and today I'm going to present you the paper CellPack Explorer Interactive Model Building for Volumetric Data of Complex Cells. I wrote the paper together with Ludovic Autumn and Graham Johnson, who are the two developers of CellPack, and Thomas Theusner-Wehr and Thorsten Möller, who also work in the field of visualization. During the work of this project, I was supported by the University of Vienna and the visualization group there, which is led by Thorsten Möller. The University of Vienna is located in Austria and Europe. For today's talk, I will start with a brief motivation for the project, then introduce the CellPack algorithm, which is the tool that our program builds on. I will explain you the workflow the current developers of CellPack are pursuing to develop the model. I will continue with the CellPack Explorer program. This is the work of this project, and I will conclude with some work for the future. For the motivation, CellPack is a model building algorithm that interactively builds geometrical models of human cells. The development of algorithms, of model building algorithms, are a very common task in science and also happen in other domains. Another common task is the comparison and analysis of geometric output models. Since all the outputs of CellPack are geometric, this is a task the developers are pursuing. And we also wanted to support the developers in the collaboration. Since they work remotely geographically, it is not always easy for them to discuss and talk about experiments. As I said before, CellPack is an algorithm that interactively builds geometrical models of human cells. In the example I'm going to use to explain the algorithm, we will use the HIV virus. It's also a virus that is very common in science and also a lot in the media, but right now not as much as the coronavirus. So first of all, CellPack starts by having defined a volume and the surface of a volume. In this example here, you can see the shape of a sphere and an inside container, which is colored in blue on the slide. Then this volume is filled with some molecular ingredients. These ingredients are to mimic biological proteins. You can see different ingredient types here. The ingredients then get placed inside the volume by an packing algorithm. So the volume is split up into a regular grid, and each molecule gets a position proposed on the grid. Depending on the input parameters the proteins have, they either accept or reject this position and say, I don't want it and I'm not fitting in here. There are also other input parameters, for example, global packing parameters, where you can specify the granularity of the grid, so how close ingredients possibly can bind together. This is what an output model of CellPack, for example, looks like. Here we can see, as I said before, the HIV virus. I'm going to explain some different parameters. There's a parameter that controls how closely an ingredient type binds to the surface. You can see this since all the green ingredients here bind closely to the surface. Another parameter defines how closely different ingredient types bind together. You can see this here as all these blue spots on the outside cluster closely together and also are located on the surface of the sphere. To develop the CellPack algorithm, which is still happening, the developers start with a specific version of CellPack. Then they run an experiment where they sample the input parameter space and generate a lot of output data. All these outputs are geometrical and hard to compare. They start the CellPack algorithm and compute all the outputs, and when all the data is ready, they go and compare all the different outputs. The computation can take up to days, depending on how complex the output model is and how many runs they want to see. Then, when they analyze the data, they either know that they have a correct algorithm or they go and change the CellPack algorithm. They analyze the data by comparing it to domain knowledge, data from publications, or pictures they have from the microscope. The goal of this project was to support the developers in exactly that workflow. We have set up CellPack Explorer, which has two different interfaces. First, we have an input interface. In this interface, the developers can set up and run an experiment. They can specify which parameters should be sampled and in what range. Then, CellPack Explorer starts the CellPack model and computes all the outputs. When all the output data is ready, we show the analysis interface. The analysis interface is split up into 3 panels. We show the input parameters in combination to all the output cell models and a column with derived metrics. For example, we show the packing time here. Since this is a measure the developers want to have as short as possible, since a faster computation is easier for future users of CellPack. Here you can see the input interface of CellPack Explorer project. It is set up with different panels. The first panel is to choose a recipe file. In the recipe file, the packing volume, so what we saw before, the sphere and this blue container, are specified. Also, all the ingredient types and their input parameters, including with values, are defined here. In the second panel, which is collapsed on this picture, developers can set different parameters for the experiment. For example, how many packings should be computed. Panel number 3 and 4 are to specify which parameters should be sampled in what range. They are split up in 2 different panels. The first panel, 3, is to set the global packing parameters. As I tried to explain before, here we can, for example, set the granularity of the grid, which is called smallest protein size. It is sampled between 0 and 100 here. The next panel, number 4, is to set up sampling for ingredient-specific parameters. These ingredient-specific parameters model, for example, the behavior of proteins. The parameters that are sampled here are the molarity, which is the parameter setting how many copies of an ingredient could be placed in the volume, the rejection threshold of that ingredient, which controls how likely an ingredient will reject the position it gets proposed on the grid, and the jittering of an ingredient, which specify how much an ingredient is able to rotate to better fit inside the proposed space. Finally, in panel number 5, we just set where on the server the data should be stored for computation. This is what the output interface looks like. It is split up and set up in a table structure. In each row, we can see a statistical summary of all the output runs that have been computed in an experiment. The developers can create new rows and make the rows different by setting filters on the different output metrics. In that example, in group 1, the developers have set a filter on high packing time to explore which parameter setting caused this long time. Different columns show different metrics of the output. For example, the leftmost columns show the input parameters and how they have been sampled. In that experiment, we have sampled the smallest protein size, which is the granularity of the packing grid on the leftmost side, the jittering of the ingredient, which you can see here. So that was how much an ingredient can rotate. The rejection threshold of that ingredient, how likely it rejects the position it gets proposed, and the molarity of the ingredient. All the bars on the x-axis show the values, and on the y-axis they show the frequency. So how many runs of this row fulfill that value. There are some light gray and some dark gray bars. The dark grays are the ones that are active in that row, and the lighter gray is just the global values for all the runs of that experiment to provide context. On the rightmost side, box C, we can here see some randomly chosen output that is active in that row. In that experiment, the developers have just packed spheres, or better said, circles on a regular plane to have a faster computation and explore the parameters. Next to it, we can see a heat map that shows the probability, so how likely a space will be covered by an ingredient. The brighter it is, the higher the probability. The middle columns, 1 to 5 in box B, show the different derived metrics. This bar chart shows the packing time, and we can see here how there has been a filter set on the high packing time. This column here shows the usage of an ingredient, so how many copies of that ingredient have been placed in comparison to how many should have been placed. Next to it, we can see how much space an ingredient occupies of the packing volume, and this column shows just a tree of the ingredients and how they have been packed. In that experiment, only one ingredient type is placed. And this is a chart that is not really useful in that example because there is only one ingredient type, but it shows the distance of different ingredients. Here we can see a zoomed in version of 2 rows. And again, the upper row shows all the experiments, all the runs, and the lower row shows just the ones with the high packing time. The developers wanted to find out which parameter setting causes this long packing time. In the next example I'm going to show you, we will explore a parameter that controls the binding probability between 2 ingredients. We can see 2 different values here. The left side shows a high probability of binding the red circles to the gray circles. All the gray circles packed closely around the red circles. The opposite is on the right side. Here we can see all the red circles and how the gray circles loosely pack to them and are placed somewhere else. Here we can see a zoomed in version with 2 rows having the outputs of a simplified HRV model. In the upper row, we can see a ring in the projection heat maps, which shows that all the ingredients have been packed regularly around on the surface of a sphere, so we have the projection of a ring. The bottom row shows the opposite. The value of the ingredient binding is set to a higher value, and we can see brighter spots here at the top of the sphere. In the future, we want to expand the CellPack Explorer project and provide, for example, different sampling strategies. At the moment, ingredient parameters and global parameters are only sampled regularly. We also add the possibility for the developers that they can include customized derived metrics if they want to explore other derived metrics in the center column. And we want to include an automatic clustering algorithm so that different rows by default are proposed already. Thank you for your attention, and I'm here to answer any questions you may have now.
Thanks to you, Magdalena, for this presentation. We have ample time for questions. I give the floor to anyone. Maybe we can start with a question from me about, maybe you could say to what extent this modeling is physics-based.
It's always based on the input parameters. So the developers are currently still adding input parameters or deleting some or changing the behavior. And these input parameters model the physical properties. Actually, I'm not sure if that was your question.
To some extent, yes. But can it be used to generate lots of data so that you can simulate data that are acquired by scanners, etc., so that you can train deep learning networks?
No, no, there's no machine learning included at the moment.
No,
it's only the parameters they manually create.
I understand, but my question is, if you want to generate synthetic data for deep learning methods.
Oh, you want to use CellPack to generate data for machine learning? Yes, this would be possible. You would just either, you could change and run different experiments, so changing the input parameter values, or you leave them all the same and then you get still different outputs because the model works statistically.
So for what kind of tasks would this be suitable?
I'm not sure. You could use any task you want. You could just use the packing algorithm also for other data. You don't only have to compute biological cells.
Can you, for example, also make synthetic slices of these cells to simulate tomography slices?
Yes, this should be possible.
And then it comes into, then it gets important to simulate also artifacts of electron microscopes, for example, namely that they also generate noise.
Yes, I think that should be possible. Since I'm not the expert of CellPack itself, because I've worked on CellPack Explorer, which is to explore CellPack. So I can't give you a lot of details about CellPack. It's also quite a while since I've been working on that. But I think CellPack should be able to do that.
Okay. Any other question? Maybe a last question also related to the evaluation of the other methods in this session. To what extent is there the notion of ground truth? How can you sort of measure the quality of your output with respect to some golden standard?
No, that's not possible at the moment. You would have to do it manually and could just compare it using CellPack Explorer. You could compare it to the main knowledge or a golden standard, but you would have to do it manually.
Yes. All right then. If there are no further questions from the participants in this session, then I want to thank everyone, all the participants, also all the presenters. A big thank. I want to close this session by saying that there is, of course, the Discord where the conference has the server for all presentations. So you can look at it later. This session is also recorded, so you can look it back. Thank you, everyone, and hope to see you back in the next session. Bye-bye.
Bye.